Welcome to Weller Physics, where physics meets medicine to save lives. In this deep dive, we'll explore how X-rays, CAT scans, and PET scans can be used to create powerful images of the human body, and then we'll explore how radiation therapy can target cancer at its core. This is Medical Physics. X-rays are used for a variety of applications in medicine. X-rays are generated through a process involving quantum mechanics and electrons around the atom. So ultimately what happens here is we use an X-ray tube to generate X-rays to be either used for imaging or radiation therapy applications, but X-rays can also be generated with things like linear particle accelerators or synchrotrons. The process by which X-rays are generated starts with a filament that is heated to eject electrons toward a target. The electrons accelerate toward the target and interact with that metal target, ultimately shifting around the energy dynamics of electrons within the target or the anode material itself. And some anode materials are like tungsten, copper, or molybdenum, among other metal materials that can be used for X-ray generation. These incoming electrons essentially interact with the target to change around the energy levels of electrons within the target, causing them to excite and relax, emitting X-rays. And then we can place a detector beyond some sample that we're trying to emit X-rays through to pick up where the X-rays actually made it through and back calculate out some type of image from where the X-rays were blocked out by the sample. In the process of sending an electron toward the metal target, we generate several different types of photons as this electron beam interacts with the target. The most common form of photons that we get are called breaking radiation. This is essentially background radiation that is generated as we try to generate specific characteristic X-rays. This background radiation is sometimes called Bromstrelung radiation. Essentially, this breaking radiation is a result of the electrons being deflected by the nucleus within the target material. But these electrons don't actually interact with other electrons in the target. It's like we have a beam of electrons just being shot toward a target, and they bend their path around the positively charged nucleus without actually leading to any electronic transitions taking place within the orbitals of the atom. But as these electron beams change their direction, there must be some work done on those particles, and so energy has to be conserved. And essentially what happens is as those electrons deflect, they kick out a photon of a variety of different energies depending on how strong the deflection is. This Bremsstrahlung radiation can be shown on an X-ray spectrum as this large lobe-like shape. We get a range of photons emitted according to this breaking radiation, but there ultimately is a energy cutoff or a low wavelength cutoff where we no longer get any breaking radiation at all. And we can calculate the energy maximum of photons that are emitted through breaking radiation through this equation right here. That would correlate with the lowest wavelength of photons that we get when we're trying to generate these X-rays. The lowest wavelength would correspond to the highest possible energy photon that we could get from this process, and that can ultimately be calculated based on the accelerating voltage that we send these electrons toward the target at. We accelerate electrons, which have a charge of E, using an accelerating voltage delta V acceleration, and that leads to the ultimate maximum amount of energy that a photon could have from this breaking radiation. But we could have a range of energy values by this breaking radiation process. We contrast the breaking radiation with characteristic X-rays, which occur when the incoming electron beam interacts with the target material such that it kicks out one of the electrons from an inner shell of that target material. We have an incoming electron that hits another electron from the inner shell of that target, causing for a higher energy electron within the target to relax down into that vacancy. And in that process, a photon is emitted, and that photon has an energy that matches the energy of the transition for that relaxation process. So essentially, a inner shell electron is kicked out by this electron beam, leaving a vacancy, and a higher level electron will relax down into that state and emit a photon with a characteristic energy. And remember, these energy levels within an atom are dependent on which atom we're talking about, how many protons there are. And that's why different targets like copper or molybdenum or tungsten will have different characteristic X-rays that are emitted. So we can have a variety of different transitions that take place, each with their own characteristic specific X-ray energy that would be emitted with that photon. And so we can label these different relaxation transitions by determining what shell the electron will ultimately relax down to emit this photon. We use a letter to designate the final shell that the electron is jumping down to, and a subscript that denotes which transition this specifically is. So let's take a look at an example. The K alpha is the first possible characteristic X-ray that we want to start with, that we could get, and that would be a relaxation from an n equals 2 shell to an n equals 1 shell. If we jump down from the second energy level to the first, that will be a K alpha transition. And if we jump from the third N shell to the first N shell, we're still arriving at the first N shell for our N final, so that is a K transition, but we would call that the K beta transition because it's the second possible transition that could relax down into the K shell. And K gamma and so on, K gamma would be an N initial of 4 and an N final of 1, and so those are the K transitions, and they keep going up with the Greek letter alphabets from there. Usually you won't have many more than alpha, beta, or gamma. But we can also have transitions that end up in a different shell other than 1. If our N final is the second energy shell, we can relax down from the third, and that would be corresponding to the L alpha X-ray that is emitted. The L beta would be a transition from 4 to 2. And then M alpha would be the next set of X-rays that we could get, and that would be like from 4 to 3. And M beta would be 5 to 3, and so on. So we can label each of these different characteristic X-rays based on what electronic transition they correspond to in the atomic structure of the target. And so in our X-ray spectrum, we had the lobe-like background radiation as that big lobe at the bottom, but characteristic X-rays appear as sharp peaks, and we can label each of those K alpha, K beta, K gamma, L alpha, L beta. These correspond to different N final numbers and different electronic transitions within the target that is generating these X-rays. Okay, so let's give this example a shot. Here we have an X-ray spectrum that's been given to us, and this is for tungsten, and we are asked to calculate the wavelength of the K alpha and K beta X-rays that are generated from this target, and also determine the lowest wavelength of the breaking radiation with an accelerating voltage of 100 kilovolts. So we have several different X-ray spectra here. The red line would be at 50 kilovolts. If we accelerate our electrons at 50 kilovolts, we'll notice we actually don't get any characteristic X-rays, just maybe a little bit of breaking radiation as that low energy electron beam interacts with the target. But then as we step up to higher accelerating voltages to 75, we're starting to see the characteristic X-rays come up a little bit. We're getting into that energy range where those transitions are possible, but really the best sample is this 100 kilovolt line, and we'll see the big, broad Bromster-Lung radiation background lobe, as well as some characteristic X-rays. And notice that we have photon energy here. So this is not in terms of wavelength on this graph. Whether it's in terms of wavelength or energy will be up to the problem, and both of these are perfectly legitimate ways of presenting an X-ray spectrum. So first, let's try to find the K alpha peak. That's this one right here. Technically, there's a little bit of a doublet nature to this peak, but you don't need to worry about that. We're just going to take that value, and we're going to say that it is right around 59 kilo electron volts. That's the energy of that X-ray. And let's see, K beta over here, that's going to be slightly higher energy because it's coming from a higher initial N numbered shell. And we'll go ahead and say that that one is about 67 kilo electron volts for that. Okay, so we can take a look at each of these transitions and figure out what the wavelength would be of that photon. We have a K alpha that has an energy equal to 59 kilo electron volts. And so we can go ahead and calculate the wavelength of that transition of that X-ray using our HC over lambda that we know from quantum mechanics. So calculating lambda should be relatively doable from here. And I can also calculate that for K beta. And so whether we calculate that in meters or nanometers, we will find that this is in the range of the wavelengths for the X-rays in the electromagnetic spectrum. And now thinking about the background radiation that is generated in this process, we can find the lowest wavelength would correspond to the highest energy X-ray that was emitted. And so if we take a look at the black graph, we can see our lobe-like shape has a maximum energy right around 100 kilo electron volts. That's the highest energy of the photon that is emitted as we try to generate X-rays. So we can match that up to our equation And that would correspond to 100 kilovolts for our accelerating voltage. And the energy of this photon will also correspond to a specific wavelength for the highest energy background radiation that we'll get in this process. And so there's our solution for the highest energy photon, lowest wavelength photon that's emitted through background breaking radiation. And you might be required to interpret some of these X-ray spectra to pick out which peaks are which and calculate either accelerating voltages or wavelengths or energies from the spectrum. X-rays attenuate the same way that all waves do through a medium. X-rays attenuate as they interact with matter, which means that they essentially die off or lose intensity as they pass through an object. And this intensity decreases exponentially according to exponential decay with the penetration depth, according to Beer's law, which we've seen previously for other waves like sound passing through material. Here, mu is the linear attenuation coefficient in inverse meters, x is the penetration depth, and I0 is the initial intensity at the start of some reference point, and I, as a function of x, is the intensity after we penetrate through a certain penetration depth. The linear attenuation coefficient depends on the half-value layer thickness. This is essentially a definition of how deep into a material we would have to penetrate before the intensity is reduced by half. And according to these exponential decay functions, we can calculate that half-value layer thickness and relate it to the linear attenuation coefficient by taking the natural log and dividing it by the attenuation coefficient to give the half-value layer thickness. This X-ray attenuation process can be used to create images of objects, or essentially also to use X-rays to send radiation into a tissue or material a certain depth. And there are three main attenuation processes that X-rays undergo as they interact with biological tissue. First, the photoelectric effect, which is when photons are interacting with electrons within the material itself. And this photoelectric effect dominates for low energy X-rays as they pass through a material. Essentially, this means that photoelectric effect is very useful for imaging heavy objects versus light objects, like bones versus soft tissue. Compton scattering involves an X-ray interacting with an electron in the sample such that the photon gives some of its energy and momentum to the electron without actually kicking it out of the material. And this Compton scattering dominates the attenuation processes for mid-range energies. Pair production is a high-energy process where high-energy X-rays spontaneously delete and turn into an electron and a positron. This is called pair production. It's essentially a nuclear reaction that takes place when a photon annihilates and turns into a electron and positron. This is especially present for high energy X-rays, and so that is where pair creation ends up dominating the X-ray attenuation processes. So this isn't as useful for medical imaging because these photons pass straight through materials, but this is useful for radiation therapy where we're trying to deposit high amounts of energy into a sample. These different attenuation processes can be used for medical imaging, and conventional X-rays essentially were used for a long time to use essentially a negative image of the X-rays that made it through to the detector to back calculate out an image. But there are some problems with two-dimensional conventional X-rays. They don't actually allow us to see through the bones themselves or the heavy dense material. We can just see where a dense material is and where a light material is, but we can't really distinguish throughout a dense material where the separate objects are. And also, conventional X-rays use a divergent source, so we can't actually get accurate measurements of size. The picture that we get on the back end depends sort of on how we set up the source and the object to absorb this radiation. So computer tomography, or CAT scans, are a new type of technology and technique that is used to create a three-dimensional image of the body using X-ray imaging. A CAT scanner uses a circular detector and emitter system to send X-rays through a sample and ultimately calculate many, many slices of the object and back calculate out a 3D profile to eventually show us an image of the inside of a biological sample. While this tool is extremely useful for generating high-resolution images of medical processes, it is highly time-intensive and also involves high radiation exposure. Another similar technique is PET scans, positron emission tomography, which essentially uses a positron electron annihilation reaction to measure gamma rays that are emitted from a localized site. By injecting radioisotopes into a sample, they can decay and ultimately create positrons through that decay that recombine with other electrons in the sample to emit gamma photons. And by this annihilation process, the gamma photons have equal energy in opposite directions. And so utilizing the symmetry of that reaction, we can ultimately use this PET scan to calculate an image of where that annihilation site took place and get a very high resolution image inside of a biological sample. Specific energies of radiation are considered to be ionizing. Ionizing radiation is capable of ionizing a sample and ultimately changing around its chemical or electronic structure. This mostly takes place through Compton scattering. This ionizing radiation can be measured using a Geiger counter and essentially utilizing the activity of a sample to determine how many reactions are happening per second and what type of radiation is being emitted by this. Ionizing radiation damages DNA by ultimately creating free radicals in the biological sample. The ionizing radiation has so much energy that it causes for water molecules to split into these highly reactive species. And those highly reactive species in the biological solution will react with DNA and ultimately lead to damage on the DNA. This damaged DNA can be repaired by a variety of processes, but also the damage in DNA through the repair process and ionizing process can lead to mutations that ultimately can lead to long-term damage for that biological organism. We can have point mutations or cross linkages that can be broken or reconnected at the wrong points, mismatched, and ultimately double strand breaks that can all lead to harmful biological effects for an organism. The radiation dose describes how much energy is deposited by ionizing radiation into a specific sample of a certain mass. And the dose is measured in units of grays. Actually, it's measured in a variety of units like grays, sieverts, which are both the same. They both mean 1 joule per kilogram. But some legacy units include rads or rems, Röntgen equivalent man, as well. So you'll usually want to stick with sieverts, but sometimes you'll be given numbers in these other units as well. The radiation dose is essentially calculated by taking the energy that is deposited into a material divided by the mass of the sample. And so this will give you a joules per kilogram, and that denotes your dose. And different doses of radiation can lead to harmful or non-harmful effects. The radiation exposure depends on a lot of different factors, but one could be the activity of the radiation source. The more radioactive it is, the more exposure a sample would have to that radiation. But that energy that is deposited by the radioactive source diminishes as we get farther from the source, and it diminishes in a 1/r squared inverse distance squared relationship, just like the energy of all waves. Different types of radiation are more or less harmful for biological organisms. And so we can calculate an equivalent dose, which is essentially a modification of the absorbed dose that we saw in the previous slide. So this is still measured in grays or sieverts or any of the other units, but it is modulated based on the type of radiation that's interacting with the biological sample. Here we see that a gamma ray interacts differently with biological cells than an alpha ray does. An alpha ray has many collision points that causes a lot of damage as it passes through a biological sample, but perhaps a gamma ray doesn't quite cause as much damage. It's like gamma rays are less harmful to biological organisms than alpha rays are. And we quantify this effectiveness by talking about the relative biological effectiveness, the RBE, which essentially tells you how effective different types of radiation are at dosing a biological sample. And so we can calculate the equivalent dose by taking the absorbed dose and multiplying by the relative biological effectiveness for a certain biological species that absorbs this radiation. And some values for the RBE for different types of radiation are given. We'll see that alpha particles can actually do a lot of damage because they're very large and very heavy as they try to pass through a sample. Okay, so here's an example of a biological organism absorbing radiation as they work at a weapons plant. We're asked to calculate the equivalent dose, so that's going to be DEQ is our question mark, in Röntgen equivalent man per year, some pretty weird legacy units here. And this person inhales and retains an activity of 1 microcurie of 239 plutonium in an accident at the plant. And the mass of lungs affected is 2 kilograms, and the decay, every single plutonium decay emits an alpha particle with 5.23 mega electron volts of energy with a relative biological effectiveness of 20. So there's a lot going on here. Let's go ahead and write out our equation for the equivalent dose as being RBE times the dose absorbed. Well, the RBE is not so hard, but I haven't been told exactly what the dose absorbed is yet. So let's go ahead and take a look at that. That is going to be the energy deposited per mass. That's the total energy deposited per the mass of the sample. And so we're talking about this person's lungs. The mass of that sample is going to be 2 kilograms. But the total energy is not just 5.23 mega electron volts. This plutonium sample has an activity of 1 microcurie. So we got 1 times 10 to the minus 6 curies. And we know in every 1 curie that there is 3.7 times 10 to the 10 becquerels, which is essentially decays per second. And that's in every single 1 curie. So that'll get us out of curies, right? And bring us into decays per second. And we know that in every single decay process that we emit an alpha particle that has 5.23 mega electron volts. I'll go ahead and put that into electron volts for now. And that's for every alpha decay. We have that many EV. And then finally, we are also going to expose this person to this radiation for basically a year. That's going to be our time interval that we have there. So that's 1 year. Or if we change that to seconds, that's 3.15 times 10 to the 7 seconds in every year. So that'll be our time interval. And let's go ahead and see what we get for our dose absorbed. So for my absorbed dose for this person, given these conditions, I'm getting 48.8 Roentgen equivalent men. Notice that I converted from EV to joules, so I could be in sieverts, joules per kilogram, and then I just multiplied by 100 to get to those legacy units of Roentgen equivalent men. And so now we can calculate our equivalent dose. And so I'm getting a result of 975 Roentgen equivalent men every year. While radiation dosages can be harmful, they can also be used for radiation therapy or radiotherapy, where we're using radiation to specifically target one area of a biological sample to ultimately damage that tissue without damaging the surrounding tissue. This is often done by sending X-rays or gamma rays toward a localized area in the body, and they are concentrated at one area from multiple angles so that we can target a localized area without damaging the surrounding tissue. Another way of doing this type of radiation therapy is through brachytherapy, which involves placing a radioactive sample directly on a problematic area in a biological sample. For example, we could place iridium seeds directly on the prostate to treat a patient with prostate cancer, and these iridium seeds will decay by beta decay, ultimately leading to emission of photons because of that beta decay leading to positron electron annihilation. For this reason, it's important to have limited short exposure times through brachytherapy methods because it is not a very targeted type of way of releasing radiation into a biological sample. A similar type of therapy involves proton therapy, which shoots a proton beam toward a particular area in a biological sample. These are accelerated using advanced scientific equipment like a cyclotron to extremely high energies. And these types of facilities are highly expensive, and the procedures are very expensive and often not paid for by medical insurance. These protons have a much larger mass than electrons or X-rays or gamma rays, and so these protons are capable of emitting a large amount of radiation, and they need to be accelerated to high energies. These protons essentially emit a wide range of energies because they experience a lot of background braking radiation. The protons slow down a large amount due to this braking radiation, this Bremsstrahlung lung process, and that leads to a Bragg peak, which is at a very specific location of penetration depth for these protons. That essentially means that these protons are depositing radiation at a very short penetration depth into a sample based on where we concentrate them, and this can be a highly effective radiotherapy technique. But at the same time, all of these radiation techniques involve exposure to radiation, so it's sort of a double-edged sword, and we always want to minimize the damage that we're doing through radiation while still maximizing the benefits for our medical patients. Some ways that we can protect from radiation exposure are by reducing the intensity of the radiation source, essentially by reducing the amount of radioactive material that we have to deal with or the intensity of that radiation that's emitted. We can protect ourselves from radiation exposure. We can also limit exposure time, where the dose is proportional to the time of exposure. We can also increase the distance from the radiation source, where the dose is proportional to the inverse distance squared. But another way that we can limit exposure to radiation is through shielding. Shielding essentially means we put a material between the source and the biological sample so that it does not experience as much intensity of radiation. And essentially this works by utilizing attenuation to cause the radiation to die off as it tries to penetrate a material. But the material that is used must be matched to the type of radiation that we're trying to shield from. Alpha particles and gamma particles penetrate through different types of materials, so the shielding depends on the radiation that we're experiencing. And while radiation is harmful, it can still be used for advanced medical applications. And so we use dosimeters to keep track of the dose that medical professionals are experiencing when they're working around radioactive equipment. Epidemiologists study how diseases can be mapped out to the population on a broad scale using statistical techniques. And it turns out that in epidemiological studies, we can very easily determine the statistics around cancer rates and other incident rates if we have a large amount of data. And so we would say that there's a reliable region for once we get enough samples or enough incident cases, we can eventually determine the rate at which these diseases will come up in a certain population. But for when we do not have many cases, we would be in this low confidence region on the left. And so we have to extrapolate these trends that we see at the more reliable region down to lower regions if we're trying to say what happens to someone who's been exposed to a very small amount of radiation. We can tell pretty easily what the rates are for large dosages of radiation, but for small radiation, we have to use statistical models to estimate the cancer risk of such exposures. And the most dominant model for predicting low exposure risk is the linear no threshold model, the LNT, which essentially uses a linear model to map out the reliable data down to a 0 point, as if patients were to be exposed to zero radiation. We call this the low exposure risk region, and we do have some data for such cases, but we really do not have much data for low radiation exposure risk and mapping out the rates of cancer risk from there. We can think of previous radioactive sites and utilize cases from patients in those areas to help draw conclusions, but the epidemiology is not completely figured out by this point. The linear no threshold model allows us to extrapolate to lower risk regions by essentially assuming a linear trend. Ultimately, this linear no threshold model for the relationship between cancer and low risk radiation exposure predicts about 10 to 15 cases of cancer per 1,000 people exposed to each sievert of radiation. So we can sort of use this to predict how much cancer we think will come up based on someone's dosage. In this example, we see we're looking at radon-222, which is ultimately formed by a decay reaction from uranium-238. So at various places throughout the world, like Austria and Minnesota and Michigan, there are these radon caves where people visit because these caves are said to ameliorate chronic inflammation and pain in the body. This exposure to radon is said to have some medicinal purposes. And so we can say that every time a person visits the cave for an hour-long session, they experience an equivalent dose of about 2 millisieverts of radiation, so that's not very much. Let's estimate the cancer risk in cases per person that visit the cave based on our linear no threshold model. These problems often will end up just thinking about the units and trying to figure out what number they really want us to get to in the end. But here we're told we're trying to get to cases per person. And so we'll start with the number that we were given, 0.002 sieverts, and we can multiply that by the incident rate, 12.5 cases per 1,000 people exposed to every sievert. And so from here, we can calculate this, and I'm getting 2.5 times 10 to the minus 5 cases per person. And so we can basically say that the chances are about 1 in 40,000 cases will occur for every visit to this cave. And so maybe if the pain that it alleviates is worth it, you could go ahead and visit these radon caves, but that determination of the risk is ultimately up to you. So that'll cover everything for our unit on medical physics. I hope you realize that this journey that we've been on all led to this moment and led to our final farewell. And so while I will not see you in the next one, I wish you the very best of luck in your future endeavors. Take care now.